In this physical layer, the most important thing is the wire. That means the cable which we use. So we have various standards. One is standard Ethernet which supports 10 Mbps, and we have fast Ethernet which supports 100 Mbps, and Giga Ethernet which supports 1 Gbps, and 10 Gigabit Ethernet which supports 10 Gbps. These are the different standards used in Ethernet. Standard, fast, gigabit, 10 gigabit. So now mostly in labs we are using this fast Ethernet because getting 100 Mbps is something difficult. Going for 1 Gbps and 10 Gbps maybe takes another couple of years. So if you look into the standard Ethernet, okay, how they can implement, what are the cables they can use? We already seen all these cables earlier in the first unit. We have so here they're using a thick coaxial, thin coaxial, UTP, unshielded twisted pair, and fiber, 10 base here. Here 10 means 10 Mbps speed, baseband 5 means 500 meter support, 10 baseband 200 meters. Actually it is 185 only, but they will write as 200. And here T means twisted, and here F means fiber optic. So these are the various standard Ethernet implementations. All these things are cable based. All these things are cable based. And these three things are copper. Copper, they use copper wire, and this one uses fiber optic. So these things we already seen earlier. Coaxial cable and twisted pair. Cat key, cat by cat. I think you know what is cat key. Cat means category. So these are the various categories in UTP, unshielded twisted pair. So these are the distances supported by these cables. In case of thick coaxial, 500 meters, thin 185, twisted pair 100 meters, and fiber optic 200 meters. But actually, fiber optic there are so many variations are there. Practically, it supports more than two. Even it supports up to 5,600 meters also. But for example sake, we are given here 2,000 meters. Now, the another important thing is encoding in standard Ethernet implementation. Encoding means how the signal is encoded. We have a nice diagram here, we can understand very easily. So we have two different types. One is Manchester encoding, and the second one is differential Manchester encoding. The difference is in Manchester encoding, each bit period is divided into two equal intervals. The binary one bit is sent as high at the first interval and low in the second interval. The binary zero is just reverse. First low, then high. Let us see here. Suppose now you want to send a data stream or a data frame which consists of 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, something like this. Okay. And now, how you can send this? How you encode it when you pass on through the transmission cable? So it happens like this. 1 means high, 0 means low. You know all these things, right? High 1 means high, 0 means low. That's it. Now let us see how this Manchester encoding is happening. It was already stated here. In case of 1, it moves from high to low. High at the first and low in the second. So you can see whenever 1 is there, this goes from high to low. Whenever 0 is there, it moves from low to high. And here high to low. And here high to low. So wherever ones are there, it moves like this, high to low. Wherever zeros are there, it moves from reverse, low to high. So this is the way of Manchester encoding. And but here the thing is you require more number of bits. For every bit you have to specify either from high to low in case of 1 or low to high in case of 0. But in case of differential Manchester, they reduced this the transitions. Here you can see in case of differential transistor, the transition occurs only when see you can see here in differential Manchester encoding, one bit is indicated by the absence of transition. That means if there is no transition, that is taken as 1. Okay, at the start of the interval. If 0 bit is indicated by the presence of transition, means if you have 0, here the transition occurs. If you have 1, nothing happens. It just stays as it is. So no transition, 1. Yes transition, 0. You can see this. In case of 1, it is 1. That's simple. In case of 0, there is a transition. You can see it's moving from low to high. This is the transition. This transition occurs only when there is a 0. The same thing here, same thing here, same thing here. But when you come to here, this is 1. So there is no transition. It's straight away coming like this. So these two things you have to keep it in mind. 1 bit is indicated by the absence of transition at the start of interval, whereas 0 bit is indicated by the presence of transition at the start of the interval. These two lines you have to remember. Based on this, you have to look into this uh, encoding and encoding figure. So that is about Manchester encoding and differential Manchester encoding. Uh, then comes the most important part, that is Ethernet frame format. Let us come to this Ethernet frame format. Let's look into this thing. So this is the Ethernet frame format, and this is important in the examinations also. So let us first see the various fields which exist in this Ethernet frame format. It is also called as MAC frame. In this, you can see it begins with preamble. The preamble is 7 bytes. This preamble is 56 bits, 7 to 8, 56 bits, and there are always alternating ones and 0, 1 0 1 0 1 0 1 0. Basically, this preamble is important for the synchronization. So that is why they use 1 0 1 0 1 0. That's a standard in any Ethernet frame. Then comes SFD. SFD means start frame delimiter. Means this SFD tells after this SFD the destination address comes. The SFD is also always standard, and its address is 10101011. The last two digits, look at them carefully. 10101011. So that 11 is mandatory. This is placed in this SFD field, which is a 1 byte. You have 8 bits there. And then after SFD, you have the DA or destination address, 6 bytes. And then you have the source address from where the frame is originating, and destination address to where the frame has to go. And then comes length or type. We will look into this length or type. There are two different methods. And then comes data and padding. This padding is important here. We look into that also. And finally, the CRC. The CRC meant for to find out whether this frame is intact or not. The receiver should know whether the center, the frame from the center came intact or not. To find that, it uses this cycle redundancy check, which we have seen in error detection. So they'll use this CRC, which is 4 bytes. Now, so these things are straightforward: destination, source address, assembly, and preamble. But these two you should look into a little bit closely. The thing is, data, minimum data. I'm showing that. Uh, yeah, yeah. Here you can see the minimum data should be 46 bytes. If any case, if your data packet is less than 46 bytes, what you have to do? Then you have to add some unnecessary bits, which is nothing but padding bits. So for example, if your data is 43, say for example, but the minimum payload length is 46, that means there is shortage of 3 bits. The 3 bits, what are the 3 bits you are adding? Those bits are called as padding bits, and you always have to maintain 46 mandatory. So whenever your data is less, then only the padding comes into the picture. If your data is more than 46 bytes, there's no need of giving any padding. And the maximum size of the frame, maximum size of the payload is 1500 bytes. You can't cross 1500. That is standard in Ethernet. So that is the meaning for this data and padding. So the padding issue comes only when the data is the length of the data byte is less than 46 bytes. So starting with 46 above, you don't need any padding. And then let us come to this length or type. This length or type, see, basically the maximum length of the value is below 1518 or above 1518. Why they say 1518 means the length of this payload is maximum is 1500 bytes. And later you count these things: 6 plus 6, 12, 12 plus 2, 14. 14 plus 4, 18. So 1500 plus 18. So this is the 1518. You can see 1518. If it is less than 1518, it defines the length. Okay. If it is less than 1518, it defines the length. If it is more than greater than 1518, then it defines the type. So that is how the type or length comes into the picture. You got it? So less than 1580 it denotes the length, more than 1580 it denotes the type. And of course, for the type we have other subfields which we look into later. So that is about these things. Now you have to remember carefully. Preamble, this is for synchronization, which uses 56 bytes, sorry, 56 bits in the form of alternates ones and zeros. And we have the start frame delimiter or SFD, which holds 8 bits and 10101011. That's important. And followed by destination address, which is referred as SA, followed by source address SA, followed by length or type, means less than 1518, more than 1518, and then followed by data and padding. If it is less than 46 bytes of data, add the padding. If it is 46 or above 46 bytes, no need of padding. And finally, the CRC, which is meant for checking the error control. So that is the explanation for this Ethernet frame. That's it. Yeah, you might get a doubt that why we should use a minimum frame as 46 bytes. Why can't we put a less number also? The thing is, actually, they designed this in such a way that diagram. I don't. There's no diagram. This is actually the time in Ethernet. The time is 51 microseconds. Means, say for example, if this is the station A and this is the station B. Now the thing is, when the first frame reaches this destination, the front part reaches this destination, the end part should be here. If not, what happens? Maybe another station might send another packet, and that may lead to collision. So when the length is exactly calculated, then automatically it always puts the busy signal, and this avoids the collision. Because when other station when they start sensing, they feel that the line is busy. So for that length, they maintain 512 bits, which is nothing but 51.2 microseconds. And of course, the maximum length it is taken as 1500 bytes. It's the Ethernet standard. Because the reason why they fixed up with 1500 bytes, you might ask why 1500, why 1500, sir? Why can't you put 3000, 4000? The problem is, see, basically in those days when they came up with this Ethernet, the memory is very, very expensive. So when the packet is moving from one router to another router, and if you're putting larger size, the router should have more memory to hold it, because until it reaches the entire frame, until it receives the entire frame, it can't retransmit it. That means in the meantime it has to store it in its memory. So, but its memory is limited. So for that purpose, in those days, they fixed the maximum size of the payload to 1500 bytes. Plus, anyhow, there are 18 bytes for control. Total comes to 1580 bytes.